the 27th, but I thought I'll try to squeeze in enough reality to be useful over the next over 3 lectures. So the game plan, and we'll see how we do, is today to go through the essential cosmology and to discuss the stellar mass binary stars as sources of gravitational radiation. Next time we'll do supermassive black holes in the centers of galaxies as sources of gravitational radiation. And finally, on March 3rd, do compact objects around supermassive black holes as sources of gravitational waves. My suspicion is that there's a little bit more to say about the binaries and about the others, so I may run over a bit in the discussion of the binaries, since I decided I should tell you a bit about the cosmology. So the thing you'll notice in common about these 3 classes of gravitational wave sources that I'll tell you about are that they're all essentially binary point masses. And those are the simplest, the most robust, and the most calculable gravitational wave sources, and calculable in 2 senses. First of all, you can calculate the gravitational waveforms, at least in the Newtonian or post-Newtonian limits, extremely accurately. And also, the sources are quite clean. You can understand their evolution. You can actually observe the progenitors. And we can understand quite a lot about them. And that's in contrast, for example, to things like R modes or mountains on neutron stars or collapsing supernovae with bars and other things which we have no idea how to calculate from first principle, and honestly, and the uncertainties in both, and perhaps some combination of the event rates or the amplitudes of the sources can be uncertain by 10 orders of magnitude. Now, in many of these cases of the binaries, of course, we don't understand, we can't predict the event rates to 3%, but we can probably predict a lot of them to a factor of a few, which is quite different from many orders of magnitude. So we can do better than an order of magnitude in many of the source rates. And so from that sense, they perhaps may not be the first sources which gravity wave observatories see. They're probably exotic things we haven't thought of, but they're the ones that we understand best, can calculate, and are sort of the ground truth for any gravity wave observatory. So today the plan is to do those that are descended from stellar mass binaries, and I'll just give you a warning that although the evolution of isolated single stars is fairly well understood, except for pesky things like mass loss and what happens to stars between 8 and 12 solar masses, and it's fairly well understood because it depends mostly on calculable physics, hydrostatic equilibrium, nuclear physics, radiation transfer, and opacities. The opacities were the hardest part up until a few years ago, until Lawrence Livermore Lab devoted considerable effort to actually calculating the opacities from first quantum mechanical principles. And now the opacities are in really pretty good shape. So things like mixing and stellar rotation and mass loss and so on are pesky problems, and we don't understand what happens in degenerate carbon ignition. But otherwise, we can do the evolution of a non-rotating spherically symmetric isolated star pretty well and understand what happens to it. However, the evolution of interacting binary stars, and we don't, as gravity wave sources of 2-point masses, one star is by itself is not good enough. We need 2 of them. And in particular, we need 2 of them which are interacting, because as I'll show you, the stars which are born with separations large enough that they don't interact are not very interesting as gravity wave sources, and the ones that we care about are the ones which interact and change their their properties dramatically so that they become interesting gravity wave sources. And those interactions are intrinsically 3-dimensional hydrodynamical processes which are not calculable in detail at the moment with any computers. Not only it's not just hydro, but it's radiation hydrodynamics. And it's quite sensitive to poorly understood aspects of the mass loss and mass transfer. So if you sort of go at it from the point of view of trying to take reasonable initial conditions of stars in the galaxy and then do theoretical evolution forward, it's quite uncertain because we don't actually know all the input 3-dimensional physics. On the other hand, electromagnetic observational discovery of the relevant compact binaries is quite different, in some cases impossible. And even when it's difficult, it's rife with selection effects and incompleteness. These are difficult observations, they're very faint sources. So the observations don't give us as good a handle as we want, but with some combination of the theory and the observation to paper over the gaps in each other, as I said, I think we can do better than an order of magnitude. So that's the best we can do at the moment. The predictions of the source numbers are maybe good to an order of magnitude, but that's much better than for any other gravity wave source. So let me tell you about those. So let me first just give you a number which you sort of were asked to calculate something like this in the homework, and I gather some of the homework is optional, so perhaps not all of you did this. But let's just suppose that we have a binary consisting of two one-solar mass stars. Then you will find that if you put an orbital period of 12 hours, half a day, that Kepler's laws, m is omega squared a cubed, tells you that the semi-major axis is 2.4 times 10 to the 11 centimeters, which is 3.4 times the radius of the sun. And for the non-astronomers, the radius of the sun is 1/4 of a degree at an astronomical unit, so that's 7 by 10 to the 10 centimeters. Now, the gravity wave frequency, if this is in a circular orbit, let's say, then gravity waves will come out as the second harmonic, so 2 over p orbital, and that is, in this case, 4.5 by 10 to the minus 5 hertz. And the merger time scale, I've cleverly chosen these numbers, so the merger time scale is exactly 10 to the 10 years, approximately the age of the universe. Now, the merger timescale decreases very rapidly as the orbital period decreases. So stellar mass binaries with orbital periods that are much less than half a day will have lifetimes much less than the age of the universe. So in steady state, there won't be any in the universe unless they're continuously being created today. On the other hand, binary stars with orbital periods much longer than several hours will have lifetimes longer than the age of the universe, and therefore will never get to frequencies that would be of interest to either LIGO or LISA or any gravity wave experiment, which is currently under serious consideration. They'd all have orbital frequencies well below 10 to the minus 5 hertz. Okay. So there's something very important about these our orbital periods. It divides the ones which will, in the age of the universe, sweep up to high frequencies and enter the LISA or the LIGO frequency bands, and the sources which will never enter them in the current age of the universe. So another thing, and I'm not sure. So Kip can tell me if you've written. Have you seen this expression, convenient mnemonic, for the amplitude of the gravity waves from a binary of mass m1 and m2?
Something like that. Gravitational potential energy is basically the source of it.
Right. So this is the distance to the source, and this is the semi-major axis of the binary, and up to factors of order. Right. So this is the amplitude of the gravitational wave produced by this binary at this frequency. So if you substitute in Kepler's law, which tells you that Gm1 plus m2 is 2 pi over p orb squared times a cubed, which is pi times the frequency of the gravity wave squared times a cubed. If you take the cube root of this and stick it in here, you're going to write this is proportional to the chirp mass to the 5/3 times the frequency to the 2/3, and I'll suppress this GW here, divided by R, where mu to the 5/3 is m1, m2. And the luminosity of gravitational waves is like the time average h dot squared, so that's the flux, times r squared. And so that's like c to the 5th over g times mu to the 10/3 f to the 10/3. If you substitute in here, h dot will be like f times h, and we square that. And we'll use units for g equals c equals 1 usually, so we'll forget about that. I implicitly did it because there's some, I assume g and f were dimension. Product was dimensionless. So this is the time, so if we have a binary whose evolution is being driven by gravitational radiation, then that gravitational wave luminosity from it is the time derivative of its orbital binding energy. So again, substituting in Kepler's laws into here, the cube root of this expression, that's something like dropping the g's and the pi's, mu to the 5/3, f to the 2/3. And if we differentiate that, that's f dot, f to the minus the 3rd, mu to the 5/3, again dropping the factors of order unity. And so now we need to equate these, and we find that f dot is proportional to f to the 11/3 times the chirp mass to the 5/3. And the merger time scale, which is proportional to f over f dot, is proportional to f to the minus 8/3 mu to the minus 5/3. Okay, so this is the important scaling. Now you know I gave you one example. If I have a pair of 1 solar mass objects, the gravity wave, for a gravity wave frequency of 5 10 to the minus 5 hertz, the lifetime is 10 to the 10 years, and now you can scale to any frequency you want, or any mass combination you want, just using this equation. And notice the f to the minus 8/3, this is really pretty steep. So if I go to 4.5 by 10 to the minus 2 hertz, sort of at the upper end of the LISA band, that's 1,000 times up in frequency, so that's a factor of 10 to the 8th in lifetime. So the lifetime of a 1 + 1 solar mass object with an orbital period of order a minute, so gravity wave frequency of order 4 10 to the minus 2 hertz, will be 10 to the 2 years. And if I go up another bit, sort of the bottom end of the ground-based limit, another factor of 1,000 to 45 hertz, I've lost another factor of 10 to the 8th. So I've gone from 100 years, which is 310 to the 9 seconds, to 300 second lifetime. Okay. Remember, this is sort of the bottom end of the LIGO band. So the ground-based observatories are interested in the last 3 minutes at best for stellar mass objects. Now, the other thing to notice about this is that if I have a population of sources which I'm creating at some long period like this one, so let's suppose I create a population and that I'm in steady state. So let me be interested in those sources which actually manage to merge in the age of the universe, so they get up to LISA or LIGO frequencies, and therefore they have to be created by some messy astrophysical process that has nothing to do with gravity waves. It's creating them with orbital periods much less than 12 hours. And therefore, their lifetime against gravitational radiation will be much less than 10 to the 10 years. So, since the universe is more than 10 to the 10 years old, they'll be approximately in a steady state. Then we could write that d by df of the number density of those sources in the universe times their frequency derivative will just be the injection rate, and let's suppose we stick them all in at some frequency f injection. So n dot will be the rate at which we're creating them with frequency f injection. Then for f less than f injection, we'll just have the steady state, which says that n of f is equal to n dot over f dot. N dot is now something independent of frequency, it's just the injection rate, and f dot depends on f. So up here, so this is proportional to n dot f to the minus 11 thirds. Okay, or the so this is the number per unit frequency. So the number per log frequency, the number per octave in frequency, fn of f, is proportional to n dot f to the minus 8 thirds. And that should be sort of obvious, right? If I'm injecting the sources, if the population has a lifetime which is proportional to f to the minus 8 thirds in steady state, the number that are around is proportional to their lifetime, right? The number of 1-year-olds in the human population is approximately 1 year divided by the mean lifetime, 80 years. So 1 out of 80 is the percentage of 1-year-olds in a steady state population. If it's different than that, then it's not a steady state. This is the frequency at which I'm creating the sources by messy astrophysical processes, which start them off as two-point masses, which then start interacting just by gravitational radiation. It's the frequency at which the source is born as a pair of point masses, at which God creates these 2-point masses, and I'll discuss how God does that. Or at least theoretical astrophysicists do that. And God does it in the Milky Way at approximately the rate that theoretical astrophysicists say, so one or the other of the two is right.
Theoretical astrophysicists took the heat before they did it.
Why, Kip, how cruel, yes. Okay. So, in addition to the lifetime becoming extremely short, we can also see that the number of sources that we expect at 10 to the minus 4, 10 to the minus 5 hertz, the number of sources that we expect here is going to be 5 orders of magnitude larger than the sources at 4, 10 to the minus 2 hertz, and 10 orders of magnitude larger than the number of sources at 45 hertz. Exactly the same factor. So for every 10 to the 10 of these, we have one of these.
I'm confused. I'm confused about this DFD. The DF of the stuff equals n dot. What is that equation saying? What is otherwise?
It's otherwise known as the continuity equation. You recognize right? Usually you put 0 over here since you think mass is conserved, but if it weren't, there would be a source function. Right?
So that's an S of F. What is? Right. I guess I don't understand what is the letter there. It's n dot times.
This is a delta function.
So it is a delta function. What's that?
Yeah. So I'm just saying, suppose in principle there's some hideous source function, but let's consider those sources that are born at some frequency S injection. Then there's this. Now you could imagine some more complicated one, and then you'd integrate over the green using this as the Green's function.
Yeah, so all you've done there is just integrate over some.
Well, I've just integrated this equation, which says that n of f dot is n dot. Right. So if I had a range of F injection, then I would just have an integral of this, and I would have this for F less than F injection, and I'd integrate the range.
I mean, it's really for F equals F. I mean,
No, this is for any F less than F injection. Because the F dot, remember the sources, so imagine frequency. Okay, the source, F greater than F injection, sorry. So the sources are being injected at F injection, and then gravitational radiation is inexorably leading them up until they merge. And of course, this will break down at that frequency at which the two objects touch. Or,
it was the direction of the inequality.
right, yes, this is, sorry. Orbital period less than.
Yeah, right. I understand that.
Okay. Okay. So just to remind you of some sizes, of course. The types of stars of which we're most interested will be, let's say, ordinary main sequence stars. And the radius of a star of one solar mass is on the main sequence. One solar radius. And for stars of other masses, it's approximately linear in the mass, but not quite. We'll be interested in white dwarfs, and the radius of a typical white dwarf is about the size of the Earth, so about 5 by 10 to the 8th centimeters, and it scales approximately as the mass of the white dwarf to the minus 1/3, but in fact, as the mass of the white dwarf approaches 1.4 solar masses, the radius actually goes quite rapidly to 0, so I'll give you a better approximation for that. There are neutron stars whose radii, and I should say white dwarfs, have masses between 1.4 solar masses, which is the maximum mass of a stable white dwarf, above which it will collapse to a neutron star, and they can exist down to 0.01 solar masses, at which point they stop being called white dwarfs and start to be called Jupiters. Neutron stars have radii of about 10 to the 6 centimeters, the size of Pasadena, and the mass is 1.4 solar masses, and probably they can exist for a range of about 0.3, about that, although we don't actually know the equation of state, so we don't quite know what the allowed range is. And finally, there are black holes whose radii you all know how to calculate. And they can exist, so far as we know, for any mass, although it's quite hard, actually, we believe, to make them with masses less than those of neutron stars or white dwarfs, because otherwise they would be neutron stars or white dwarfs. So usually astrophysicists are unconvinced that anything is a black hole unless the mass is larger than about 2 solar masses. And in fact, all the objects that we know about, which are like 1.4 solar masses, show hard surfaces and nuclear burning on the surface and other signs that they clearly are white dwarfs or neutron stars. So we can use this result that we derived here on the merger lifetime to construct a sort of interesting diagram where we put mass and solar masses along one axis and log of the binary semi-major axis, say in centimeters along this axis. And if we choose our axes, so one solar mass, we'll do log and log. So we'll have one solar, 0, one solar mass and 10 to the 10 solar masses here. And we'll put 6 centimeters and 10 to the 16 centimeters up here. And anything down here is otherwise known as a, I'll give you a hint of color, I colored it in my plot. Right. So you can't have binaries of this mass smaller than this, because it's two black holes orbiting each other. So on this diagram, let's see, let me introduce. So 6, 11. So we can put in neutron stars live about here. White dwarfs live in the range of a little bit below a solar mass and 10 to the 9 centimeters up to a little bit above a solar mass and 10 to the 7 centimeters. Oops. Have white dwarfs, and then main sequence stars live here, solar radius. Okay, so we have a lower limit to the size of a binary containing 2 white dwarfs, or 2 main sequence stars, or a pair of neutron stars. And of course, if you have a neutron star plus a main sequence star, the binary size is limited to that of the larger star. So it's interesting on this diagram to actually draw the lines of constant frequency and lifetime. So let's see. So 10 to the 2 hertz looks something like this. 10 to the minus 3 hertz starts at 10 to the 10. Here goes. And 10 to the minus 8 hertz starts. Okay, so this is sort of LIGO, LISA, and pulsar timing, frequency bands. And the lifetimes are somewhat interesting. So we start off here, 10 to the 11. So here is 10 to the 10 years. And you'll see that crudely, the main sequence tracks a lifetime of order 10 to the 9 years. So you cannot have any binary system containing a main sequence star has a gravitational wave lifetime which is greater than about 1 billion years, and also has an orbital frequency which is less than about 10 to the, or a gravity wave frequency less than about 10 to the minus 3 hertz. So there's no way 2 main sequence stars are ever going to be detectable by LIGO. They might barely, for very low masses, be detectable by LISA. Merger time of 1 year. Runs along through here, so through the white dwarfs, and merger time of 100 seconds starts over here. So you can see that pairs of white dwarfs have a maximum frequency. Let me just write down the maximum frequency for white dwarfs, it's 0.04 times the mass of the white dwarf in solar masses over the mass of the white dwarf. And for black holes, this is for Schwarzschild black holes. Quadrupole is 4 by 10 to the 3 m-son over m hertz. So that's essentially when this frequency line intersects the size of the stars. So pairs of white dwarfs or neutron stars can happily radiate at 10 to the minus 3 hertz or even 10 to the minus 8 hertz. They're just very wide binaries that are widely separated. On the other hand, pairs of white dwarfs are never going to be radiating in ground-based detectors. The two white dwarfs are touched by the time they get even to a few hundredths of a hertz. So that means that the sources that are of interest for ground-based detectors are limited to these two. And if we go over here and remember that the lower limit for the frequency band for the ground-based detectors is around 100 hertz, you can see once again that we're limited for the ground-based detectors to sources down here. And that means that the lifetimes are, even for the lowest masses, less than 100 seconds and typically rather much less. So you're interested in very short-lived sources, which are very rare. On the other hand, as you go to the space-based observatories like LISA, 10 to the minus 3 hertz, you see that you can look at stellar mass systems whose lifetimes are like 10 to the 8th, 10 to the 9 years. So you can have huge numbers of them. And that's a big difference because it means, if you remember that our galaxy is making roughly one star every year, and some fraction of those are binaries that will do interesting things, at the ground-based frequencies, remember we're losing, compared to our 10 to the 10 years, we're going up a factor of 10 to the 6 in frequency, so we lose 10 to the 16. So we have to, if we make one star a year in our galaxy, there's a probability of 1 part in 10 to the 6 that we'll see one of these in our galaxy. That means we need to look at 1 million galaxies in order to see one of them in a year. On the other hand, if you go to 10 to the minus 3 hertz, this minus 8/3 power buys you a lot, and that factor of 10 to the 5 gets you up to a order 10 to the 8 sources in the galaxy alone. Rather than having to look at 1 million galaxies to see one source, you can now see 10 to the 8 sources in our local galaxy that we live in. Okay, so if we want to quantify these results a little bit, I thought I would assume that most of you are physicists who have absolutely no idea what the universe is made of, and therefore give you a little bit of an overview of the cosmology and explain how you go about, if you know. So I should point out that I'm going to be talking about stellar mass binaries today. And there is one galaxy in which we understand stellar mass binaries, and that is the one we live in. We know a few stellar mass binaries in the satellite galaxies of our own, the large and small Magellanic Clouds, M33. We can see some neutron star binaries and a few white dwarfs in them. But that's it. So if we're going to start talking about having to look at 1 million galaxies or calculate a background from the whole universe, we have to understand all the other galaxies and have some idea how to extrapolate into it. So that means we need to do two things. The first thing is a sort of Copernican principle, which is although we're very special and we happen to live in a galaxy and not in a random place in the universe, we will assume that everything that happens to the stars in our galaxies is just like all the other galaxies everywhere else in the universe at all times, for all metallicities, for all environments. It's probably not true, but since we don't understand star formation and evolution well enough, that's about the best we can do. And there's indications that perhaps it's not too bad. We can look at different environments in our galaxy, and there don't seem to be very big differences. And the second thing we have to do is we have to understand if we're using our galaxy as a representative sample of all the stars in the universe, we have to understand what fraction of all the stars in the universe our galaxy really is. So that's the part that I will tell you about now. Okay, so the cosmological overview, you all know, and it's been in the newspaper, so it must be true, the universe is flat. So the universe is flat, which means that the density of something is equal to the closure density. And the critical closure density, 3/8 pi 1 over g h naught squared is 1.17 by 10 to the 11 solar masses per cubic megaparsec. So those are convenient units for this purpose. The other thing, it is true because I say it is so, h naught is equal to 65 kilometers per second per megaparsec. That's true today in this room, and probably within 7 or 8% it's true everywhere for the foreseeable future. So, and this assumption has gone into calculating this number, of course. Now, of this critical density, 70% is dark energy.
Yeah, physics, and we don't know what the numbers are made of, so we don't. Several people denote different things with H naught. What is your H naught?
Oh, I'm sorry?
What is your H naught? Hubble constant?
Here.
But is that the Hubble constant?
Yes.
Because different people denote different things with H naught. So.
Okay, all astronomers use H naught to mean one thing, which is the Hubble constant. So, okay. It's the only symbol used for that quantity so far as I know. Okay, so 70% of this critical density is in dark energy, which we have no clue what is, but probably is not stars. And 30% of the closure energy is matter, by which we mean stuff whose equation of state is density goes like size to the -3. And unfortunately, of this matter, well, of that 30%, 27.5% is dark matter. And again, we have no clue what that is, but it probably almost certainly is not baryons, but is supersymmetric particles or something or other. And the grand total of 2.5% of this critical density is actual baryons of the sort you know and love and study solemnly in physics. So the other 97.5% of the universe, we don't have no idea what it is yet. Now, of those baryons, only a small fraction of them are accessible to most astronomers. There are a few very sophisticated astronomers who study the rest of the baryons, but most astronomers study stars and galaxies, which are a pathetically small percentage of these. And so of this critical density, about 10% of these baryons are actually in stars. So that's 0.25%. 10% of the baryons, 0.25% of the critical density is in stars. And the rest of it, the other 2.2%, is in gas. Okay, so of this grand total of critical density, 1/400th of it is in stars. So that's the part we're talking about today. And we're talking about a small percentage of those stars, too. So don't get your hopes up. Now, of that 0.25% stars, so of the stars, and I actually changed my, so I should say, yeah. When I write 0.25% here, some people, a lot of people in the literature, use a convention where this number is 0.35%, but they all know that that convention is wrong. It's just a convention, which is due to Ed Saltpeter in 1955, and everybody knows it's completely inconsistent with the data, but it's a convention, and so you should really take all those numbers and multiply them by 2/3, and I've multiplied them by 2/3 there. So that's the real fraction of stars. It has to do with the initial mass function, which I'll get to in a moment. The luminous stars by which you determine this are only the stars that you actually see, are a tiny fraction of the actual stars, and so it's all the pathetic little 0.1 solar mass stars which dominate the mass density. And so the question of how you go from the 5 solar mass stars that you see to the 0.1 solar mass stars that are most of the mass is the issue there. So of the stars, the universe contains about the following: about 76% of the star mass is in luminous stars, and most of those have mass less than the mass of the sun, because the sun has a lifetime of about the age of the universe, and stars more massive than that are no longer luminous if they were created early on, and most of the stars in the universe were created a long time ago, and therefore have turned off if they're more than 1 solar mass. 18% of the star mass is in white dwarfs, quite a substantial part. Something at the very best, maybe 2%, is in neutron stars, and maybe 3% in black holes.
That 3% includes galactic mass black holes?
No. This is all stellar mass things. Yeah. Yeah. No. We'll do the galactic ones next time, but they're a much smaller fraction than that. But they're about 0.1%. They're more impressive individually, but not in total.